and he'll be telling us about his project, Formalizing Matroids.
All right, thank you, Heather, for the introduction, and thanks to the organizers for giving me the chance to speak. I'd also like to thank Heather, who I've known since we were teenagers, for giving me a call out of the blue 6 months ago to chat and mentioning formalization, which I've always been curious about, and that was kind of the nudge I needed to start doing it. So I'm a mathematician. I'm interested in Matroid theory. I have a very limited background in anything computer sciencey. The same can't be said of my two collaborators, Ed and Matt, who are very mathematically inclined, but also know a lot more about programming than me. So we wouldn't have got far without them. I also like to say this project is kind of in its infancy. We're still making design decisions, and some of them are probably wrong. So I want to apologize in advance for anything I say that's too naive or grandiose sounding. And I need to finally mention, as far as I know, there's been no formalization work done on Matroids before us, except by Brian Chen, who did some things a few years ago. Even though we didn't base our code on his, it was a really good reference, and it was really good for me figuring out how lean works from the beginning. Okay, a matroid is it's my favorite mathematical object. One of the nicest ways I've heard it described is that just like a group is a mathematical object that captures the intuitive notion of symmetry, a matroid is a mathematical object that captures the intuitive notion of independence. So here's the definition. A matroid is a pair that consists of a finite set E called the ground set, and then a collection of subsets of E called the independent sets that satisfy three axioms. The first axiom is just that the empty set should be independent. The second says that the property of independence is preserved under taking subsets. So if I have a subset of an independent set I, then that should be also an independent set. And the third is this less trivial augmentation property. This says that if I have two independent sets of different sizes, where I is smaller than J, I can find an element of the larger independent set and add it to the small one in such a way that the small one remains independent. So this axiom actually mentions cardinalities of things. This is one of the many reasons that we want the ground set to be finite. I was quite surprised at how much of a can of worms it is to ask that something is finite when formalizing, but there's many reasons we like matroids to be finite. Okay, I'm sure this definition is new to some of you, so I probably owe you a couple of examples. I'll start with the one that Whitney was thinking of when he defined matroids in the 30s. What Whitney was trying to do was to capture the abstract properties of linear independence as you see it in sets of vectors in a vector space. So if I have any finite set of vectors in my favorite vector space, that will give me a matroid in a very predictable and simple way. So here is a set of 5 vectors in R3, for example. That will give me a 5-element matroid by saying the independent subsets of those vectors are just the linearly independent subsets. So for instance, in the matroid that arises from this 5-element set, this element will be a singleton that is not independent because it's not a linearly independent set of one vector, but this pair of vectors will be an independent set in the matroid. Of course, you have to prove that always gives you a matroid. If you look back at the axioms, you can see that the first 2 axioms are trivial in this context for a set of vectors, and the third one follows almost as trivially from a dimension argument. Another nice example, that a nice way to construct matroids is far more combinatorial. If you start with a graph, that will give you a matroid on the set of edges of the graph. When I say graph, I'm letting you have loops. I'm letting you have loops and multiple edges. So that might be a multigraph, depending on how you like to call these things. The matroid I get on the set of edges of this graph will be defined by saying that the independent sets of edges are the ones that don't contain a cycle in the graph. So for instance, if I take these 4 edges in the graph, that doesn't contain a cycle in the graph sense. So that would be an independent set of 4 edges. If I add this extra edge, then I now have a 3-cycle or a triangle in the graph. So that would be a dependent set of edges. It's not too hard to show that this is a matroid as well. if you look at the first two axioms, you'll see that they're trivial. And the third axiom follows essentially from some pretty simple stuff to do with how spanning trees behave in a graph. All right, why formalize matroids? I mean,
question.
Go ahead.
The first example with linear algebra, isn't it saying that putting finiteness assumption in a definition is wrong? And if you remove this finiteness assumption, then you can just talk about linear independence.
You can, but if you remove the finiteness assumption, then other important things will break. So in this particular setting, you could define infinite matroids. If you have a finite, or if you have a set of vectors in the vector space, you could talk about the matroid. But most of the machinery you'd want to prove about matroids more generally is not going to apply in such a general setting. The same for infinite graphs. You can define a matroid on infinite graphs, but you have to be very careful for a number of reasons, and also the theory will break in other places. Right, so why formalize matroids? I think that, I mean, matroids are fun. At least I think they're fun, and that's a good motivation for me. The combinatorial theory of matroids is very interesting to me. It's really the side of things I'm the most interested in. It ends up linking matroids, which are these inherently combinatorial objects, to interesting things like graphs embedded on manifolds and finite projective geometries, which I won't say much more about, but there's some really beautiful theory there. The link between matroids and graphs here is actually, it's fairly faithful in the sense that if you have some mild non-degeneracy conditions, the matroid determines the graph just as the graph determines the matroid. And because of that, there are many results in graph theory where matroid theory is actually, one could argue, the correct level of generality. So there are some theorems about graphs that are easier to prove if you rephrase them as theorems about matroids and derive the graph result, which is a good idea for formalization. Matroids also arise in some external contexts. If you take the characteristic vectors of the independent sets as real vectors and you take their convex hull, you get a polytope with some really nice properties in both optimization and algebraic geometry. Matroids also occur in algebraic geometry as a nice way to stratify the Grassmannian, and there are some deep links there to things like Hodge theory and unimodality conjectures. So I want to talk about some very baby steps we've made towards formalizing some things in matroid theory, some things that I'm happy with and things that I'm not happy with. And even if you don't care about matroids, I'll talk at the end briefly about a tactic that we're working on, which might be of some more general use for formalizing other things. All right, so this next slide, it contains 5 definitions. I'm usually not the type to put 5 definitions on one slide, but you'll see why I'm doing it in just a minute. So these are all basic words in the language of matroid theory that you need to be familiar with to do nearly anything. Most of these words are borrowed from linear algebra, so they'll be fairly familiar. If you have a matroid, then a basis of that matroid is just a maximal set with the property of being independent. So if your matroid came from a set of vectors, then a basis of the matroid would simply be a basis for the subspace spanned by those vectors that is contained in the set of vectors itself. A basis for a matroid that comes from a graph is essentially a spanning tree. So this is a fairly natural notion. A circuit is a similar object. A circuit is a minimal set in the matroid that's not independent. This is not such a familiar thing from linear algebra, but it is from graph theory. If you take a matroid that comes from a graph, a circuit of the matroid is precisely a circuit of the graph. You can also talk about the rank of a set in a matroid. Here it's defined to just be the largest independent subset of that set. That corresponds to rank or dimension in a fairly obvious way for a set of vectors, but here it's defined completely matroidally. Every matroid has a rank function that maps subsets of the ground set to non-negative integers. A flat of a matroid is another type of special subset. It is a set that is maximal having a given rank for a set of vectors that would correspond to the intersection of that set of vectors with some subspace. Finally, a matroid has a closure function which maps subsets of the ground set to subsets of the ground set, and it's some sort of linear algebraic closure-like thing, you can say it's the intersection of all flats that contain that set, and that's the way to define it matroidally. So the reason I'm defining all these things on one slide is because they all share a common property, that they all determine the matroid. So if you know just the bases of a matroid, you don't necessarily know the independent sets, you can easily recover the independent sets by just saying a set is independent if and only if it is contained in a basis. So if I'm only telling you the bases of a matroid, you still know the matroid. Similar for circuits, a set is independent if and only if it does not contain a circuit. So if you know the circuits, you know the matroid. You can also show that if you know the rank function or the closure function or the collection of flats of a matroid, that determines the matroid. So that's kind of nice that you have different ways of thinking about this matroid, but what's nicer is that they actually all give equally good definitions of a matroid. So the definition I showed you is just a choice I made. I showed you the definition of a matroid in terms of independent sets, but you can also define it just as pleasantly in terms of any of these 5 objects, and in fact, various others. This is referred to in a somewhat tongue-in-cheek way as cryptomorphism. So here is a definition of a matroid in terms of its rank function. So again, you have a finite ground set, and you have a function that assigns a non-negative integer to each subset of the ground set called the rank function, provided it satisfies these 3 axioms, where the first 2 are somewhat trivial and the third one is submodularity, that will define the same object as the independence family I showed you defines. This is actually my preferred set of axioms. It's the one we base the formalization on. And you can do the same kind of thing for the bases. So you actually only have 2 axioms there, one of which is just non-emptiness. If you know that you've got a family of sets satisfying these 2 axioms, then they are the family of bases of a matroid. This is how you define a matroid in terms of its circuits, or its closure function, or its family of flats. So these definitions are all an important part of, you need to have them all in mind when you're thinking about matroids. Some of them will be more or less natural for certain purposes. If you want to prove something as a matroid, you probably want to pick a convenient axiom set. If you want to prove something about matroids, you pick a different convenient axiom set. One of the nice things about this, if you're teaching matroid theory, is that any pair of the axiom sets are equivalent, but the equivalence is not immediate. Like you wouldn't be able to derive it in 5 minutes just by looking at the 2 axiom sets. Sometimes it requires a bit of work depending on the pair of axiom sets you're looking at. It's the kind of thing you'd give as an exercise to a graduate student.
Sorry, I have one question.
Mm-hmm.
So this definition with the basis, for instance, are you saying that to every matroid there is a unique basis such that this definition gives back the other one? So what I had in mind is simply for a topological space, for instance, you have many different bases giving the same topology.
So yeah, the matroid uniquely determines a basis, its collection of bases. So if I define a matroid in terms of the independent sets, then the bases are precisely the maximal independent sets. And so the correspondence is unique. Probably the topological notion of basis is not the thing to have in mind here.
It's a set of all possible bases for the like the vector.
Okay.
Yeah, it's the collection of all possible bases. Yeah.
Okay. So all these cryptomorphisms are somehow canonical or unique, at least.
Yes, they're canonical. A matroid will have a unique collection of circuits, a unique collection of bases, a unique collection of flats, a unique closure function, and a unique rank function.
Thank you.
And you can go between these objects.
I've not worked with matroids very much, but I've seen them before. But are they? Is there a sort of categorical equivalence between matroids and linear algebraic structures, vector spaces?
I'm not so up on category theory, but I suspect the answer is no. So something that's true is that matroids that arise from a set of vectors in any way at all are vanishingly rare among all matroids. Matroids are very chaotic objects in full generality. I wouldn't expect anything too nice and categorical to be true about them completely generally.
This particular list of characterizations of matroids that you've gone through here,
Mhm.
to me, looks almost exactly the same as our, well, not exactly the same, but analogous to a big theorem that we teach our elementary linear algebra students, characterizations of invertibility, which are very much like characterizations of bases in vector spaces. So everything that you listed looks a lot like, except the ones that are mainly in terms of graphs, looks essentially like the kinds of things that characterize bases, linear independent sets, and so forth, that you can give this kind of definition in linear algebra. And that's why I was asking that.
Right, yeah, I can see what you're saying. Yeah, maybe we can continue this. Yeah, I'd like to talk more about this. Thank you. All right, so from the perspective of formalizing, I think going between these pairs of axioms, it's a very natural thing to do. I mean, it's a good playground to start with, but also when you're doing it, you're developing so much of the basic theory and you're proving tons and tons of things which will certainly be useful later. So that's really where we've started. We're not done with this cryptomorphism stuff, but we've written a few thousand lines of code and I'm quite happy with how it's going. There's a clear path forward. So I want to show you just briefly what this kind of looks like. So this slide here has two definitions of a matroid, if you like. One of them is in terms of the rank function, and one of them is in terms of a family of independent sets. So here I've got four definitions that just say, if you have an integer valued function, what does it, this first definition is saying this function satisfies the property that every rank is non-negative. The second definition is saying that every rank of a set is at most the size of a set. And so these four definitions correspond to satisfying the four rank axioms. I kind of split one of the ones I showed you in two for various reasons. And then we've got a structure that bundles a function together with four proof terms and says, I am the rank function of a matroid. So this is what the structure is doing. It's a finite set together with a rank function on the set. And then down here, we have the same thing for a family of independent sets. So this is a kind of independence predicate on the subsets of a finite set. This first one is saying the empty set is independent. The second one is saying subsets of independent sets are independent, and so on. Then you bundle them and you get an independence family, which is encoding the same mathematical information, but not in an immediate way as the rank function. So then you have to prove something. You want to go between definition sets. So this is a summarized version of how you'd go from, say, the definition of an independence family to a rank function. This first part says what your rank function actually is. If I tell you the independence family, you need to say how I calculate the rank of a set, which is some kind of choosing the size of something. And then you need to prove that if you define the rank function that way, you have four axioms that are being satisfied. Now this fourth one is by far the longest, and there's hundreds of lines of code that I'm not showing you here for how you get there, but it's all kind of reasonable, fun stuff to write. Once you have that rank function and those four proof terms, then you now have a function which takes as input a matroid phrased as an independent family and spits out a matroid phrased as a rank function, and both of the input and the output have the bundle proof terms. Here is the kind of boilerplate I just want to show what this would look like for something we haven't done yet. This is the definition of a matroid in terms of a family of flats. So we have three flat axioms and then a collection of flats together with proofs of those axioms. That's a flat family. Then I have to have a definition of what it means to be independent in terms of a flat family. And I've got three unproved things, which are that if I define independence that way, I satisfy the independence axioms. And once I've proved those, I can go from the flat family to an independence family. And then if I like, from an independence family to a rank function, which is, again, where I want to land for personal preference reasons.
Could you tell us what is bool alg? So you're
yeah, so bool alg, I mean, this is partly my collaborators and I, struggling with lean. Bool alg is essentially a Boolean algebra together with a certificate of finiteness in terms of written as a size function. We ran into problems with using set and fin set to do with decidability and stuff that I chose not to get into for this talk, but you can think of this as like a fin set type. So this is just this is a subset of the collection of subsets of something, yeah. So it's a Boolean algebra together with certificate of finiteness. All right, so that's what I wanted to say about cryptomorphism. I think it's, yeah, as I said, we've got a reasonable way forward, and we've got some pleasant code to write and more pleasant code to write in the future. So I'm quite happy with how that's gone. I now want to talk about something I've been less happy with, and I'm not saying it's because we're doing things the best way, just because the way we're doing things, we're still running into some trouble. So this is a nice matroid concept called duality. If you have a matroid with a certain ground set, then there's also going to be a dual matroid with the same ground set. This is a very nice construction. Of course, I've shown you can define matroids in half a dozen different ways, so I can pick my favorite way to tell you what the dual is. If I have a matroid, it's got a collection of bases. The dual matroid, its collection of bases are the complements of the bases of the primal matroid. So in that one setting, duality is just complementation. Of course, I would need to prove to you that that really is a matroid, and you have to do some work one way or another, and we decided to do that work in the setting of rank functions. But what this function's doing is taking a matroid phrased as a rank function, spitting out a matroid phrased as a rank function, and on the same ground set. And to do that, I need to tell you what the new rank function is and then prove to you that it is the rank function of a matroid. But that's what this does. So this isn't itself unpleasant. This is fine, but I need to mention this for what's coming. This is where things started getting a bit difficult for us. Matroids have kind of sub-objects called minors. They're not sub-objects in a categorical sense that I know of, although there's sort of, it kind of smells of that a bit, but I don't know how to make these categorical in a precise way. If you have a matroid and you have a subset of the ground set, there are two different ways to remove that subset from the ground set to get another matroid. The first is deletion. So if I want to delete a set A from a matroid, what I do is I take a new ground set, which is just the complement of A in my old ground set, and a new rank function, which is the restriction of the old rank function to the family of subsets of the new ground set. Right, so deletion really is what you'd think it is. You just throw away some elements and maintain the structure. Clearly, this is still a matroid because you haven't changed the rank of any individual set, so the axioms still work. The other way you can remove some elements from a matroid are by contracting them. This is written M/A. To contract a set in a matroid, again, I remove that set from the ground set and take a new rank function, but this new rank function is not the same as the old one anymore. It's defined by this difference of two rank functions in terms of the set I contracted. Now I can mix and match deletion and contraction. I can do one thing, then the other, and even do things multiple times. And if I do that, what I have is called a minor of the matroid. Right, so a matroid has a family of minors. One thing to note here is that this is a bit more complicated than something like a subgroup. To tell you a minor, I can't just tell you the ground set of the minor. I have to tell you how I got there. Like I contracted this, deleted this, and so on. So we found this fairly difficult to formalize in a satisfactory way. And I'll just try to point to some of the issues we ran into. I mean, this slide is showing you some nice things about minors, but they're pointing towards some of the issues. First of all, when I contract and delete things, everything is commutative. If I contract something and then delete something else versus deleting something, then contracting something, then it doesn't matter which order I do it in. It's also true that if I contract something and then delete something and contract something and delete something else, then it's the same as contracting the union, then deleting the union. There's disjointness assumptions everywhere here, but this is true for disjoint sets C, C1, C2, and so on. Minors are also they play really nicely with duality. Contraction and deletion are dual operations. So if I contract a set, then dualize, it's the same as dualizing, then deleting the set. If I contract and then delete and dualize, it's the same as dualizing, then deleting, then contracting. Now, the reason I mentioned this in particular is because contraction and deletion are dual operations, and this is a very important thing when you're doing anything in matroid theory. So any solution to formalizing this, which does not respect the duality, is breaking a really important symmetry. So you might be inclined to say deletion is this and contraction is something else, but if you can't prove that contraction and deletion are dual, or say without loss of generality we're looking at one or the other, then you're really breaking a symmetry and making life quite difficult for yourself. So this was an important design question we had to solve. Now, I wouldn't say this to mathematicians, but if you're a computer scientist, you might care about exactly what I mean by equal. Two matroids are equal if they have the same ground set and the same rank function. And it was a rude awakening learning how complicated equality can be. So to show you what I mean by that, here are some different senses in which minors can be equal or otherwise. I could have two minors of a matroid which are equal because they're the same. I contracted and deleted the same thing. I can have two minors of a matroid which are equal because of how I define minors. So M delete 1 delete D2 versus M delete D1 union D2, they're exactly the same thing. I'm removing two sets and I do it together or one by one. You can also have matroids that are equal, but I contracted and deleted different things to get to them. So I could contract C1, delete D1, contract C2, delete D2, where C1 is different from C2, D1 is different from D2, but they happen to land on the same rank function. Those are equal, and we really want them to be equal. It follows from the definitions that if you had this equality, then C1 union D1 and C2 union D2 are the same set, but the partition doesn't have to be the same. I could still have the same minor. Now, finally, I'm not particularly happy with a solution that says, well, these aren't equal, but they're isomorphic, because you might care about two minors being isomorphic in the sense of there exists the structure preserving bijection in a different context. So really we were looking for a solution in which these three equalities are propositional equalities that I can use to rewrite rather than some kind of isomorphism with extra properties. So here is a kind of example of the kind of problem we ran into. If I have a matroid and I want to delete D1 then D2 versus deleting D2 then D1, then those are the same thing. I'm just removing two sets. But if you're not careful, they have different ground sets. They have E delete D1, delete D2 versus E minus D2 minus D1. Those are propositionally equal, but not definitionally equal. And because they're not definitionally equal, it becomes very hard to prove that the associated matroids are even propositionally equal because of type equality type issues. So this really, it was a problem. In my view, it's really unacceptable if you can't use propositional equality to denote something like this, which is so trivially true, but it was really non-trivial to figure out how to do this. So the way we'd solve the problem in this particular instance is by thinking about restrictions rather than deletions. If I, instead of saying I want to remove some elements, instead I say I want to restrict to the complement of those elements, some of these issues disappear. So you can say this matroid is M restricted to the complement of D1 and then restricted to the complement of D1 union D2. This is M restricted to D2, the complement of D2, restricted to the complement of D1 union D2. And because I kind of chose the name for where I landed in both cases, I can make them definitionally equal in ground set and therefore propositionally equal matroids. So this kind, sorry, go on.
A solution based on the model theoretic notion of a substructure anyway?
Well, yeah, I think that if you say too carefully if you say too precisely what you mean by substructure, then you run into problems with contraction and deletion because you want them to be dual to each other. I don't know a notion of substructure which solves that problem, but I'm not saying there isn't one.
The issue is type theoretic, isn't it, really? Yes. You don't really see this in set theory. So. Yeah,
in set theory, this all vanishes and nothing seems complicated. But yeah, type theory, it was very hard to make this work. So here is how we kind of solve the problem of landing on the same minor via a different route. So what we do is we decouple the minor itself from the process that got me to the minor. So this definition is this inductive definition, which is encoding a list of instructions, which is a sequence of restrictions or co-restrictions. The co-restrictions are the duals of restrictions. So I could say restrict to this set, then co-restrict to this set, then restrict to this set, and so on. This definition doesn't know anything about matroids. It just knows a set and a list of instructions. The second definition takes a matroid and a list of instructions and spits out a minor. Right. So this separating these two notions allowed us to say that two minors are equal, even if they don't look, even if it's hard to make them equal type theoretically. So here is the kind of theorem we were actually able to prove. This is, the proof is mathematically, it's a simple calculation that the dual of M contract C delete D is M dual delete C contract D. It was a huge amount of work to make the right design decisions to prove this, with this being equality and not heterogeneous equality or something else that wasn't as satisfactory. So you can see the actual calculation is here. It's not, oops, it's not really too bad. And we need some messing around here, but it's not really too unpleasant to prove this. The one reason I'm really not happy with this yet is because even though restriction and co-restriction are very natural for some applications in matroid theory, it's often not the way you think about things. For instance, you want to prove something by induction on the size of the ground set. What you do is you delete a single element or contract a single element. And if you're forced to talk about restricting to the complement of that single element, it's really not natural. I mean, you remove a screw from an engine, you don't consider the parts of the engine that are not the screw. So I think this is a practical problem for doing things and keeping things straight in your head, that you have to phrase everything in terms of restrictions and co-restrictions. That said, we were happy to get to where we were here. So in terms of moving forward for formalizing matroids, one of our intermediate goals is called the matroid intersection theorem, which is a very nice min-max theorem that tells you the maximum size of a set that is independent in two different matroids at once. That's going to have some induction. We'll need some new ideas to do that, but hopefully we can get there without too much work. And like in many areas in the long term, we have theorems that only a tiny number of people know how to prove, and we want to make sure they're correct and so on. So formalization will be good for that. I think that matroids have a kind of more elementary flavor in some ways than other parts of math, to the point where it's perhaps not so far in the future that we can formalize genuinely deep things. Okay, that's all I wanted to say about matroids themselves. To talk about my next small thing, it'll just be a few minutes. I was looking through my code for a good example of the problem that we were running into, but I actually realized there was one on this very slide. So here is a claim we proved that as part of this dual restriction co-restriction. All this is saying is some nonsense about sets. It's saying that this expression, which is constructed in terms of unions and complements, is equal to this one. There's a couple of hypotheses floating around that you need to make that true. Now, simp won't handle this. There's no really easy way to just say this is true because it's obviously true. So here's the proof. It's, 10 rewrites or something, and probably took a number of minutes to come up with that proof. It's by no means the longest such proof that's in our code, and it was getting a bit old. So we figured we'd look at a way to automate these identities involving set operations. And looking at Zulip, it seems that other people have asked this question in the past. How do I resolve this trivial goal? So I'll try to switch my screen share now to show you where I've got. Right, you can see that okay?
Yep.
Yeah, great. Okay, so
can you increase the font size a bit?
How's that?
Yeah, that's better. Thanks.
Okay. All right, so we've got this tactic. It's in a very work in progress debugging mode at the moment. And it's currently called timed simplify sets because we're interested in profiling. But it resolves these goals to do with intersections and unions that you don't want to have to think about. So here's some trivial statement about sets, and we can use this tactic and it will prove it. Here's another trivial statement, this time about fin sets, and we can do this and it will prove it. I'll comment that at this point, the finish tactic works for both of these, but it will choke on some larger examples. Here is a statement where the goal is subset inclusion. It will handle that for now. And here is the kind of thing that finish won't handle because it's not inherently propositional. This is a statement about Boolean algebra. Of course, it's isomorphic to a statement about unions and intersections, but not in a way that finish will recognize. But this tactic will handle that. This is an identity about Boolean algebras. Now you can probably see even from these examples, it's pretty slow. So here is it being much slower on an identity involving 10 sets. It takes about 10 seconds to do this in my experience. And I mean, it shouldn't be so slow. So this took 12 seconds. And that's part of the reason we're not necessarily publicizing it yet or uploading it anywhere. The reason it's slow is a reason that shouldn't really be a reason. So a statement like this about set operations, it is the same thing as some statement about propositions, right? So this other lemma here is a statement about ors and ands and negations. Of course, it's the same as a statement about unions and intersections and complements. And the Torto tactic will handle this just fine. So the reason ours is slower is because it's this homegrown free Boolean algebra object that reduces it to something that's definitionally equal. There's no reason it should be fast. Of course, Torto is developed with much more care and attention, and it's faster for resolving these things. So the difficulty we're having with actually making a usable version of this tactic is getting from something that provides a proof of this statement about propositions to a proof about sets like this, even though there's no real difference. It's the interface between those two problems is seeming like it's a bit complicated, but we're hoping to get there. We're hoping that it will handle things like propositions and handle things like hypotheses and implications in the goal and so on just fine. And hopefully it shouldn't take us too long to release something that makes a few people's lives easier that aren't just ours. Okay, that's all I have to say. Thank you for your attention.
Why don't we take time for just a couple of questions before switching over to the social hour? Anyone keen to start?
I've got a quick question. How does this tactic work? Does it convert to a ring statement and then apply the ring tactic or something?
No, so
that was my first question when I asked Peter about this a week ago. So I'm glad that someone else along the same line.
Yeah, so we did try that. The problem is that the ring tactic doesn't know that something is a Boolean ring. So it doesn't know that x squared is equal to x. And it doesn't know that 1 + 1 = 0. And you need that for the ring tactic to be able to handle this completely. So we initially had a very janky solution which involved repeatedly getting ring to simplify things as a sum of powers, and then saying, look, x squared is equal to x and 1 + 1 = 0, simplify with a rewrite, and then do ring again. And it was horrible, and it kind of worked, but it seems like the ring tactic being unable to handle hypotheses causes inherent problems. So what this tactic actually does is it maps, it goes from a Boolean algebra object to a Boolean ring, where product is intersection and addition is symmetric difference. And then in that Boolean ring, I don't want to say this wrong. Mathieu, are you here?
Hi, yes.
Hi. Okay, yeah, I'll leave
I
this
am
to
here. I'm just trying to furiously answer chat comments as well. What was the question this time?
How does the tactic work?
Oh, so currently, one way you can think about it is every identity about these Boolean algebras is the image of an identity from a free Boolean algebra with some number of, generators. And then that free Boolean algebra on a number of generators, well, you can check any identity by just essentially going through the possible truth table and checking that it always holds. So this is not the best way to do such a tactic. We're working to change that, but it's serviceable. So essentially it just checks the truth table of the identity under question.
Run into the P versus NP problem because it's satisfiability.
Yeah, so we're trying to change it. So this was our very naive attempt, and we're trying to change it to just hook into a generic, stat solver or Boolean solver, like basically make that parametric, and being able to just call as Peter has written down, like Toto. The problem is that
is Toto a stat solver or is it something else?
I think it's a somewhat naive thing that we'll just try to check if something is just
it might be complete
a tautology of proposition.
I think it's complete for propositional logic.
Right.
That's solver.
Yeah.
Interpreted generally.
And it turns out that every mathematician knows that a Boolean algebra is like the way you prove anything in a Boolean algebra is the same as the way you prove something in prop. But that actual formal correspondence is trickier than we expected.
For the set examples you have, I think reducing them to something that Toto will handle immediately is actually pretty simple, right? Now you just apply extensionality and then simplify. You get the sets are equal if and only if for all x is in one, if and only if x is in the other.
The problem with saying apply extensionality is that these are from a generic Boolean algebra, which are not necessarily sets of elements. So there are no elements to the extension over.
It doesn't work for the Boolean algebra example. Right.
Yeah.
And so the part of the reconstructing this is figuring out what elements should be for a generic Boolean algebra. And that turns out to be atoms of the lattice. But then you need some property about atoms of the lattice, which is not true for all Boolean algebras, but is true for the free Boolean algebra. So there is still some work to do there.
Okay, cool.
So I was wondering, in the end, when you want to sort of build an interface for matroids that like users can use, say if you want to apply it to linear algebra or something, are you going to pick one of the 5 or 6 definitions as the definition? Or are you going to build like a huge definition that is all of them with 6 different constructors?
I think that's a good question. My inclination is to say a matroid is a rank function, but provide easy interfaces where if you want to define a matroid a different way, then you can convert that to a rank function, which is kind of what we're doing. I'm not sure of the design implications of the other solution.
The upshot might be that you have better definitional equalities, but like when you're using it, like if I construct a matroid using independent sets or something, then I might want to know that the matroid that I actually get out of it has independent sets that are definitionally equal to what I fed into the constructor.
Right. I mean, yeah, that would be really nice, and I doubt that our approach is going to achieve that. Yeah.
Anyway,
yeah.
I also want to say that I'm really amazed. Like, if you started using Lean 6 months ago, you really did a lot of stuff, and yeah, congratulations. It looks.
Thank you. Yeah, I mean, video games have been mentioned before. And it's been like a video game at various points, but I still feel like a real amateur.
Well, I wouldn't say
this
that.
is exactly how you learn. This is how we all learned. Just getting into something and just doing it.
Yeah, I hadn't used Git 6 months ago, ever.
Wow.
Do you have plans to add oriented matroids at some point?
I don't, because I know very little about them, but I would be very happy if others did.
I was just wondering if you have proved things about constructions like circuit hyperplane, relaxation, and principal extension. Is that easy to do under this definition?
That's probably quite easy, yeah. We haven't done it, but I think it should be okay.
Because Rado's theorem can be proved with principal extension, so that might be a way to do matroid intersection.
Yeah. Yeah.
So let's leave it there and continue in the social time if need be. Rob, are you able to list the link in the chat?